I'm SalamiNaserian, and today I will be talking about the bell crank system and how it relates with all of our dynamics lectures. First, let's talk about a system overview. This system, the bell crank system, uses a servo motor which is connected to a lever arm, which drives the bell crank mechanism to convert rotational motion into lateral steering motion. The bell crank acts as a force and direction transformer. When servo rotates, it applies the torque to the lever arm, which then pushes or pulls a linkage connected to the bell crank. The bell crank pivots about a fixed point and transfers this motion to the steering linkage, ultimately turning the wheels. The key advantage of the system is that it allows compact packaging while still achieving sufficient steering force and controlled motion. We begin to analyze motion using kinematics of a particle, focusing on how a point on the servo arm moves. The main equation used is velocity equals radius times angular velocity. This equation helps us determine the linear velocity at the end of the servo arm. In this system, as the servo arm rotates, the tip of the lever arm follows a circular path. The further the point is from the center, the greater its linear velocity. We also use acceleration equals tangential acceleration plus normal acceleration. This tells us that the point experiences tangential acceleration due to changing speed, normal acceleration direction towards the center due to rotation. This is important because it defines how quickly the linkage is being pushed or pulled. For rigid body kinematics, now we talk about how the bell crank and the lever arm are rigid bodies. The key equation used is velocity of point B equals velocity of point A plus angular velocity cross position vector from A to B. This is the relation we use when we want to find relative velocities. This equation allows us to relate motion between different points on the bell crank relative to one another. Since the bell crank rotates about a fixed pivot, we can determine the velocity of the output arm based on the input arm motion from the servo. This is important because it shows how input motion is transferred into output motion and how geometry affects steering response. For kinetics, the main equation we say is the sum of moments about a point equals moment of inertia times angular acceleration. In this system, the servo applies a torque to the lever arm, which generates a moment about the bell crank pivot. This moment must overcome resistance from the wheels, friction in the joints, and inertia of the system. This explains why the system struggled. The torque from the servo was not sufficient compared to the load caused by the vehicle weight and friction. For work and energy, the work energy principle helps us understand energy transfer. The equation is used work equals change in kinetic energy. In this system, the servo does work as it rotates, transferring energy through the linkage into the bell crank. The energy is used to rotate the bell crank, move the steering linkage, and overcome resistance forces. If the energy supplied is not enough, the system will not move effectively, which matches our observed performance where the wheels struggle to turn under load. Next, for impulse and momentum. Impulse and momentum are used to analyze changes over time. The key equation is impulse equals change in angular momentum. In this system, when the servo starts moving, it applies a torque over a short time interval, creating a change in angular momentum in the bell crank. This is especially important during startup motion, sudden direction changes, and other. It helps explain how quickly the system responds to input signals. Next, for friction, friction plays a major role in the system's performance. This equation is used. Friction force equals coefficient of friction times normal force, which is the frictional force equation we use all throughout high school. In our case, friction occurs at multiple points, such as the pivot joints, linkage connections, and wheel-to-ground contact. The servo must overcome these frictions in order to move. This includes overcoming first the static friction, which is greater than the kinetic friction, and then also being greater than the kinetic friction. And because the vehicle is relatively heavy, the normal force is high, which also increases friction. This significantly reduces the effectiveness of the servo, making it harder to turn the wheels. For real application, bell crank mechanisms are widely used in real engineering solutions systems, including automotive steering systems, which I explained already, aircraft control linkages, and suspension systems. In real applications, engineers carefully design the lever arm lengths, the pivot positions, and the material strength to ensure the forces are properly transmitted and motion is efficient. Our system demonstrates the same principles but highlights the importance of proper force and torque calculations. Without either, the system will fail. In conclusion, the belt crank system is successfully demonstrating key dynamic principles, including motion transfer, force transmission, and energy transfer. However, the system faced limits due to insufficient servo torque, high friction, increased vehicle weight. All of these have a negative effect on the performance of the servo. All of these also relate to our dynamics lectures. And if we learned anything from those lectures, we would need to use these equations in this application in order to be able to prove our system works before we move on to the production process. Thank you for listening. Hello, my name